Okay, everyone, for these last parts, they're not emphasized in Klein right now. I will test you on some of the parts I think that you've had before, but otherwise, the rest of it is just for you to think about because we're going to come back to it later. So, this is on Ketoenol tautomerization. This is really important later on in chapter, I think, 22, 21, 21. Okay, so it's good to look at it every now and then. This one's really helpful for mechanism because you often see some of these steps going on, like we've talked about activating a carbonyl before. Now, if you recall from Chem 262, we talked about the keto form and the enol form, enol being an ene, carbon-carbon double bond, and an OH group. So you should be able to go from one to the other using either acid or base catalyzed reactions. So I'll walk you through one of them here. This is the acid catalyzed reaction. I'm using H plus in my mechanism. My goal is to be able to go from the keto to the enol or vice versa. Now don't forget, you also have water in solution. And what I'm doing is, these are really good practice for mechanism because you have to sort of think through it. So my goal is to make a pi bond here. So I want to maybe do a kind of elimination reaction. Here's a beta hydrogen to the carbonyl group. I'm going to use some solvent, water, that's usually present, or some kind of base if water's not available. So now you can see how I got my enol. Okay, should be able to go backwards. So maybe in a different color, I can show you how we would go backwards. You can do this in several steps, or I can just show you in one step. Grab this H, this bond breaks, maybe goes down to here, and then this grabs H plus, and then that goes this way. You probably know that the keto form is favored, so I would draw that line longer. The enol form is usually less stable, but with some compounds is actually favored. All right. You should be able also to do this for basic conditions. So we can just go over that now as well. For basic conditions, you're only allowed to use OH minus and water. Okay, so if I have OH minus, I can't activate the carbonyl, but this is a strong base, so it can actually take this hydrogen. All right, this hydrogen is acidic because of this elimination sequence here. So when you have that, you end up with this enolate ion, and then that enolate ion can pick up hydrogen from some kind of a protic solvent like water. All right, now I'm generating a hydroxide, but I'm in a solution full of hydroxide, so it's okay. And then to go backwards, I've got my enol finally right here. And to go backwards, I can use a base. Again, I can just sort of try to show the reverse occurring. And then maybe this needs to grab some kind of proton source. All right, so these are the reactions that explain how we go from keto to enol and back and forth. Okay, you may or may not have covered this, but we have with dienes, when you covered conjugated systems last quarter, hopefully you know that this is conjugated because they're alternating double, single, double bonds. We have something called a 1,2 addition and also a 1,4 addition with dienes, meaning way back when, a couple weeks or months ago, you had, something like this. And you guys probably know that, this picks up an H plus, but it could also be through resonance that it picks up this H plus. You could have a positive charge here or a positive charge here. So what that does is it creates two different kinds of alkenes. So let's say we have both of these arrows to pick up that H. Then we have the positive charge here, and your pi bond moved to the middle, and you picked up this H. That's if you have all those bonds going. Or you could probably see the resonance structure of this, where it didn't go all the way. Maybe maybe we just pick up here. Okay, so in either case, you have either 1,2 addition if you add the nucleophile. If X adds on here, that's 1,2 addition, or if X adds on here, that's 1, 2, 3, 4, 1,4 addition, because the H added at 1, then you could add it 4. 1, you could add it 2. So 1, 2, or 1,4 addition. Anyway, the point of all that is you can see that conjugation also could be with enones, or enals. That's a carbonyl containing conjugated system. And so instead of carbon, we could have oxygen here. And so there's our carbonyl. You could have a nucleophile preferentially attack here. Okay, that's what we're used to right now. But if you had a conjugated system, it could also attack here because of resonance. Now the tricky thing is some nucleophiles like to attack at the 2nd position, some like to attack at the 4th position. So, it's maybe not super clear why some do one and not the other, but here's a list of them. And I would just say that this was sort of a little bit mushy area of science when I learned it, because some nucleophiles, I guess I would make sense out of it by saying some nucleophiles are sort of hard. It's called the hard-soft theory. That means that they are smaller, maybe more densely negatively charged. Those kinds of nucleophiles tend to be Grignard reagents, organolithium reagents, acetylide, hydride, things like that. I'll write them down here. Okay, acetylide ions are the alkyne carbon ions. So anything that usually has a negative charge on a carbon. But there's some exceptions to that, of course. So softer nucleophiles, and these hard ones tend to attack here at the carbonyl carbon, which is also, this is considered a hard electrophile. It's small, it's sort of dense itself. Being right next to this oxygen, it makes it very positively charged. All right, now carbon out here is a little bigger. It's softer. It's got this resonance stabilization right here. So its orbitals look different. It tends to be compatible with things that are fluffier orbitals as well, so more polarizable. So I would think things like sulfur, like thiol, okay, SH. Even cyanide, I know it looks like acetylide, but cyanide is a bit softer. And then other carbon nucleophiles like Gilman reagent, which we haven't learned, but basically anything other than Grignards, hydrides, and these guys listed up here will tend to attack at the 4th position. With this is called Gilman reagent. We'll learn that later. Gilman reagents are also softer because they're attached to copper. Copper is large, so it makes you think polarizable. Okay, so these are like Grignard in that the R groups are the ones that attack. Okay, but in any case, it probably helps you a little bit to just be familiar now so that when you see it again, it'll be a little bit easier to understand. So the basic idea again is there's hard-soft theory. Electrophiles can be hard or soft, nucleophiles can be hard or soft. Like dissolves like, so, or hard likes hard, soft likes soft. So you want to try to use that to match up where things might attack, be more likely to attack. So with hard nucleophiles, the main point here is that hard nucleophiles tend to be more electron rich, more dense, electron dense. So they tend to be stronger bases. So Grignards, lithium, organolithium, hydrides, strong bases, right? So that means they're energetically high, so high potential energy. So notice this downhill movement. With softer nucleophiles, it's much less so, okay? So these are much weaker as bases in general. The kinetic product tends to be favored because it has a lower reverse activation energy than the 1,4 addition. Why that's important is because if I made 1,2 addition products, They can reverse, but because of this really large activation energy, they're not really likely to make 1,4 addition products. So what will happen is these will make 1,2 addition, and if these did happen to reverse, they would still make 1,2 addition reactions over and over and over. Whereas here, they're much more comparable in energy to their starting material, so their activation energies are much smaller in general and similar to each other. With 1,2 addition products, if they reversed, there's not a huge difference to then take the 1,4 route and make more 1,4. So, and since this reverse is larger than this reverse, these are more likely to reverse, and so each time you get a little bit more 1,4, 1,4, and it pools. So that's why you tend to have more thermodynamic product with a 1,4 addition. And then just start to learn what's hard and what's soft, and see if you can figure out what our predicted products would be, and whether you should add the nucleophile to the 2 position or to the 4 position. Go ahead and give that a try, and maybe use some of this information right here to figure that out. Okay guys, so just going through, this is how you apply the hard-soft theory. So for this one, organolithium, I know that this is a hard reagent, so they're gonna prefer 1,2 addition. So I just simply think of this as attacking right here, just like I normally have been doing in chapter 19. All right, so that's how I get phenyl group right here, acid workup. Now with this one, this is a soft nucleophile. This is my sulfur group right here. So that's going to, and I remember that because oxygen's smaller than sulfur. Sulfur is larger, more polarizable. So I'm going to attack that, the 1,4 position. But that's going to then move my double bond. So I need to make sure that my double bond's placed correctly. When you have this, you'll notice that actually the double bond doesn't go to the O. So it really looks like this at first. It looks like this, okay? But this is an enol, right? And so it tautomerizes to the keto form. So really you should sort of already be thinking about these things. That actually goes to this form. All right, so whenever you see an enol, you want to tautomerize it when appropriate. Okay, here this is cyanide. That's a softer nucleophile, so it attacks here. I get the enol here, and it regenerates to a keto form. This is a hard Grignard. It attacks here at the carbonyl carbon, and then works up to neutral compound. This is actually a conjugated system, but it's conjugated all around here. So it's not really counted as a 1,4 or 1,2 addition. This is pretty stable by itself. So that means this carbonyl is free to react to form the imine, just like we have been doing. The difference is if we didn't have a conjugated system completely, like in a benzene ring, what if we only had one double bond? Now we have a 1,4 addition scenario. So when I have this nitrogen, it can attack here, and then these bounce over to here, and then I make an enol, or an enal, because it's aldehyde, enal, and then it tautomerizes to the aldehyde. Here, again, this would be a 1,4 addition, because these nitrogen compounds are soft. But this is not conjugated. See, this double bond's not conjugated. It would have to be here to be conjugated. So that doesn't count. So it only has this part to react with. Okay, and interestingly enough, it's a secondary amine, so it makes an enamine, and then that's conjugated with the double bond that was there. So we made a conjugated system. And then this last one is the Gilman reagent, which I told you probably haven't covered in class yet. It's coming up in chapter 23, but it helps to know a little bit about that. These are R groups attached by copper, copper lithium, and sorry, hard to read. One of these R groups will attack, and this is a softer reagent, so it'll go for that 1,4 addition like that. And this is an R group of ethyl, so there'll be one ethyl group. The rest of this reagent, which is ethyl copper lithium, that part goes away.